Hi, my name is Ishanka Pereira and I am a graduate student from University of British Columbia. Currently, we are conducting building energy related research at Lifecycle Management Laboratory under the supervision of Dr. Kasun Hevage and Dr. Rehan Sadiq. Today, I will be discussing about a study that we conducted focusing on energy performance evaluation of multi-unit residential buildings through a life cycle thinking approach. The main objective of this study is to develop a geo-environmental level decision-making platform for MERBs, design energy upgrades through life cycle methods. And now I will dig into the meaning of that objective and what's the practical need and impact of this study. The climate change impacts associated with greenhouse gas emissions are directly related to the increasing energy consumption, resulting more fossil fuel-based energy generation. Worldwide building sector is a vital component in the goal of mitigation of this energy consumption. Therefore, various energy performance upgrade options are available in the market to enhance the energy efficiency of the buildings. However, in countries like Canada, United States, due to the vast landscape, the climate conditions are drastically varying from location to location. Hence, the commonly available energy upgrade options might not perform the same way in everywhere. In this study, 14 different geolocations were selected across Canada based on the climate zones. With careful review, 6 most popular energy upgrade options in the market were applied to a basic building one at a time. At this basic building is defined according to the minimum requirements from the National Building Code of Canada, and few inputs were taken from the BC Energy Step Code, which is the local energy code in the province of British Columbia. As you can see in the tables on the right side, the base building elements and the upgraded elements are shown. Due to the confidential reasons, all the descriptive details for the upgrades are not shown in these tables. All these 6 building models are evaluated in the above selected geolocations across the Canada. Once all the 6 alternative MERB designs are modeled for 14 geolocations, each model's performance was assessed with their annual energy savings, life cycle emission, and life cycle cost savings. The energy savings were obtained through BIM-based simulations with Autodesk Revit, while the life cycle assessment were done using CIMAPRO and EcoInvent database with RS means cost data. At the end, all 3 performance indicators were normalized with one value called eco-efficiency parameter. As a result, each alternative design received a rank based on the geolocation of the building and based on their performance in terms of life cycle emission and life cycle cost savings. As discussed, the method of this research, the final outcome is a rank for each alternative design with energy upgrades. Deriving these ranks involves a series of mathematical equations featuring life cycle emission, life cycle cost, and annual energy savings. Life cycle emission savings were calculated considering the local utility grid emission factors and electricity and natural gas, while life cycle cost savings were calculated considering the variation of local energy prices and energy upgrade equipment cost. On the right side figure, all the selected geolocations in Canada was indicated. After the mathematical modeling and equations, the ranks were derived as in the table to the left-hand side. These ranks are derived based on the normalized score value, which is called the eco-efficiency score, which is not shown in this video. All these ranks presented here are dummy ranks. The actual rank results from the research is not shown, as the correct results are under the review of a journal. Just for the explanation purpose, random dummy ranks numbers are given in this video on the left-hand side. There are 3 types of ranks, as you can see: positive ranks, negative, and some are having 0. Regardless of the sign, lower the absolute value, the rank is better. With increasing the absolute value of a rank, the performance of that particular energy upgrade option is decreasing. Positive ranks are associated with designs delivering both life cycle emission and life cycle cost savings, while negative ranks are given when life cycle emission is positive but with life cycle cost savings are negative. In other words, emissions are reduced with increased cost. Finally, zero is given when life cycle emission saving is negative, regardless of the cost saving. If an upgrade option is increasing the emissions, which does not meet the emission reduction targets at all. As an example of such design upgrade, in the province of Alberta and Saskatchewan, the upgrade option 2, which is featuring electric seat baseboard heaters, increase the life cycle emissions. This is due to S2 consuming large amount of electricity, with those provinces are having high emission factors in their local utility grids. In such cases, these alternative design upgrades are not recommended in those provinces. Anyway, again, as a reminder, these ranks are just for the explanation purposes as given as the dummy ranks and not the actual results from this particular research. Like that, based on the above methodology, provincial level or geolocation specific level decision making can be made very easily. Provincial policymakers, law and mandate developers, building code designers, constructors, and builders are a few of many stakeholder groups who can generate preliminary design idea from such a mechanism. This was a short video of summarizing comprehensive study involving energy simulations, life cycle assessments, and mathematical equations. I hope you get a basic understanding of MERB's performance evaluation and the importance of life cycle thinking in such evaluation. The detailed information is provided in a research paper under the name provided above, which is currently under review with the journal. Please refer to the paper once it is published to see the actual results rather than dummy results as appeared in this video. Thank you for watching and I hope you enjoyed the content of this video.